Okay, great. I hope it's starting to make sense. But let's move on. We haven't got to the meat yet. Let's get rid of all of this and let's discuss this RGB system. In particular, I want to discuss this hexadecimal format. You might be thinking, Clyde, why did you use this hexadecimal? The reason for me, it's intuitive, and these hexadecimal numbers are very natural to computers. Why they're natural to computers? Well, because computers store and handle binary digits. And as we'll see shortly, 4 binary digits make up one hexadecimal digit. Don't worry if you're scratching your head, we're going to get into it shortly. So the first thing we need to discuss is we need to discuss this concept of a binary digit. And in the computer world, the word binary digit is often shortened to the word bit, B-I-T. See those green letters there? Okay, well, what is a binary digit? A binary digit can only be 0 or 1. And because of this, 2 is a magic number to most computer geeks out there. All signals inside a computer have 2 and only 2 different, therefore binary values, 0 and 1. So you can kind of think of it as off being 0 and 1 being on. Or 0 can be false and 1 can be true. In computer terminology, one piece of information which can store either a 0 or a 1 is called a bit. So, in other words, a bit represents values from 0 to 1, i.e., it can represent 2 values. Put 2 bits together and you can represent 0, 1, 2, or 3. aka you can represent 4 values. 3 bits can represent 0 to 7 values, or 8 values in total. 4 bits means you can represent 2 to the power of 4, which is 16 different values. I guess we can go on ad infinitum, but the formula is simple. X bits can represent 2 to the power of X values. And this is why 2 is a number that's very important to computer geeks. These are called base 2 numbers. Just as base 10 numbers are very important to us humans. 10 fingers on our hand, 10, 100, 1,000, etc., etc. Those are very important numbers for humans, whereas a lot of computer geeks know the numbers 2, 4, 8, 16, 32, 64, 128, 256, etc., etc. And you're going to see the point of all this in a second. Okay, so that's a bit. A bit eventually becomes a byte. At some point, the early computer engineers came up with byte as the next unit above a bit. A byte is just defined as 8 bits. And this means that 1 byte can represent 2 to the power of 8 numbers, or 256 different values. And FYI, the minimum value of a byte is 0, and the maximum value of a byte is 255. Or if we want to look at it in binary form, it's just going to be the 8 bits, all being 1s. Whew, Clyde, this is great theory, but I'm sick of theory. Why does this become important for us practically? Good question. So let's jump back to our hexadecimal number. Remember, we started with a hashtag and it was followed by 6 digits. Do you remember that? And also bear in mind, as we mentioned before, the RGB system defines numbers based on their red, green, and blue values. And in the hexadecimal system, the first 2 digits are relating to red, the second 2 green, and the last 2 are related to blue. So that kind of makes sense, but let's take a look at one of these values. Hexadecimal values can be from 0 all the way to the character F. In other words, one hexadecimal digit can have 16 different values. Okay, Clyde, that's cool, but there is not only one digit for every color. I can see that there are 2 digits there. And that's a good question. Now we've got 2 digits. Each can have 16 different values. This means that 2 hexadecimal digits combined together like this can make 16 times 16 is 256 different colors. Is this kind of starting to make sense? So we know the red can take 256 different colors, the green can take 256, and the blue, which means there are 16,777,216 different shades of color that can be produced by the hexadecimal format. Woohoo! I hope this is blowing your mind. It's really fascinating. So to get back to my logic here, my statement that hexadecimal numbers are natural to computers. Why is it natural to computers? Well, simply because each hexadecimal digit, so you know the red and the green and the blue, those can be stored as 1 byte. And bytes are very convenient when it comes to the computer world. It can hold one ASCII character, and just as importantly, a byte is the de facto standard minimum data size for memory storage. And FYI, it's also the minimum size of CPU and other peripheral registers. Text is also stored as bytes. Unicode, that encompasses all scripts, is usually encoded as bytes via UTF-8. The point I'm trying to make is that bytes are very useful when it comes to computers. And this is why the hexadecimal kind of format or system to me makes most intuitive sense. And you might be thinking, cool, we can produce 16.77 million colors. Is that enough? And yes, it is sufficient. The human eye can only distinguish up to 10 million colors. So having 16.7 million is way more than enough. But you asked a good question, and to be truthful, there are other standards out there. For example, you may have seen 10-bit HDRs. This relates to color depth, with each RGB value being 30 bits, hence 10 bits per channel, rather than our 8 bits. But again, it's kind of pointless because the human eye can only distinguish up to a certain amount of colors. You know the old saying, why fix something if it's not broken? But getting back to our code, that is exactly why we wrote the function. We wanted to produce a random number, and we wanted to produce a random number up until 16777,216. Remember, the math random function, which is from JavaScript, that generates a number between 0, which is inclusive, and 1, which is exclusive. Thus, the above will produce values between 0 and 16777,215.99999. And then we used the math floor method to round down to the nearest whole number. And I did this very deliberately because now if we round to the whole number, you agree with me, we're going to get values between 0, inclusive, and 16777,215 inclusively. And that is exactly what I wanted. That value, 16777,215, will convert to hexadecimal value FFFFFF. Have I done too many Fs? They meant to just be 6 Fs. Hence, that's the highest number we want for hexadecimal conversion. And if you include that with the number 0, it does produce 16777,216 unique values. Whew, I hope this is making sense. But remember, we didn't stop here. We added the floor function, and then we also had to add the toString method. So in the next lecture, because this is getting quite long now, I want to just briefly mention the toString method and how that works. Hope you're learning a ton, hope you're having fun, and I'll see you in the next lecture.